Ну хорошо. Значит, у нас чего было? У нас был такой сетап. Значит. Окей. Нужно по-английски. Окей. Thanks. Alright, so let's recall what we had in the end of the previous lecture, which was like 2 weeks ago. So we had a vector bundle E over smooth manifold X. And we also had two curves. One curve is is defined on an interval, and it's one curve is on X, another curve, gamma tilde, is on E, and one curve is a lift of another curve, so meaning that pi of gamma tilde of t is gamma of t for any t from this interval. Also, we talked about extensions. So S is extension of gamma tilde. It means that, well, first of all, S is what? It's a section of T, right? Such that if I consider its values at this curve gamma of T, this will be exactly gamma tilde of T. And then we said that gamma tilde is called parallel with respect to gamma if this happens. So, well, we need to fix, also of course we need to fix nabla, which is connection on E. So this is our connection. If nabla Vs equals to 0, and this is for every, well, I need to, so this gives me a section, right? And this section I consider at points gamma of t equals to 0. For any t from 0 to epsilon, and here S is extension of gamma tilde, and V, which is a vector field on X, so this is an extension of gamma prime of T. So this is a curve in Tx, right? And V is the extension of this curve. And then we obtain the following formula. In this setup, in all these notations, we obtained that nabla Vs equals, so we have this formula, sum over beta, gamma beta prime of t plus sum over alpha and over a, and here I have gamma alpha tilde of t, gamma a prime of t, and here I have Christoffel symbols, alpha, a, beta. So I have to put parentheses like that. and here I should write as beta. So here I need to well, S beta, the local basis of sections, of gamma of E, well, around some point. Gamma corresponding to differential symbols. Symbols. Also, for Christoffel symbols, we need to fix coordinates, and so we fix them, and this gamma with subscript are values, like are components of gamma in these coordinates, right? And so gamma tilde beta and gamma. So A prime, so these are components. Well, I need to write without prime here, like that. So components of gamma tilde and gamma respectively. So, okay, so this I have to remind because I will go from here. Okay. So there's this proposition, proof of which I actually postponed to seminar. So proposition. Well, which says, okay, so if I fix my curve, gamma, in the base, and I fix a point at the top of initial point of this curve. So also fix, I don't know how to denote it. Let's denote it as 0. So this is belongs to the fiber of E at gamma of 0. Okay. So fix this, fix that. Then there exists actually unique curve gamma tilde. So this is a curve in E. Well, which is parallel with respect to gamma. So let me put it here. Such that gamma tilde is parallel with respect to gamma, and gamma tilde of 0 is minus 0. All right. So this is okay. This is one of the problems in seminar. Basically, I need to apply compactness of interval and some type of Cauchy problem from differential equations multiple times. Basically, parallel means that you have a well, PDE which is given by this thing goes to 0, right? With some initial conditions which are given by this as 0. So that's what's going on. But still, I need to state this to make sense of the following definition. again, I fix curve in X. The smooth curve. And then for each t from this interval, let me define linear map from where to where. Well, my fibers are vector spaces, so I define a map from E gamma of 0 to E gamma of t. In this map, I will denote tau t. So I define it as follows. Tau t acting on a vector v here is actually the value of gamma tilde of t, where gamma tilde is from previous proposition when S0 is v, right? It's the unique curve right? Well, gamma tilde from 0 epsilon to E parallel with respect to gamma, and also gamma tilde at 0 is my V, well, which I picked from here. Okay, and so I define it, and now I need to give the name. So the map tau t is called the parallel translation. So basically now we have a way, if we have connection, we have a way to compare vectors in different fibers. All right? Окей.
А можно секунду назад?
Вот здесь?
Спасибо.
Yeah, I also said that it is a linear map, is it? So I guess I need to go back again. So is it clear that this is linear? No. That V is an initial condition, right? So I need to make sure that I have linearity with respect to initial condition. So one thing to notice is that this is a linear differential equation. So this, well, it's differential equation for gamma tilde, right? And gamma is just gamma prime is just known function, right? So it's a linear differential equation. Therefore, if I have some solution with some initial condition, if I have two solutions, then linear combination of the two solutions is again solution. All right. So that's why if I have two solutions with two initial conditions, to make solution with initial condition which is sum of them, I just sum these two solutions, and this goes. This is why this map is linear. No, I talk about sum, but also you can multiply by scalars in the same way. Okay. Another thing to notice is that this is actually an isomorphism between vector spaces. So this map is invertible because I can take this gamma, and well, I can now well take my t and well change a variable such that t of 0 is epsilon and t of epsilon is 0, right? Just change the direction of the curve, right? And then apply the same definition. Because of the uniqueness in our previous proposition, this will be inverse of this map, right? So this is actually a linear isomorphism. So note tau t is a linear isomorphism. Okay. Now, so now we're going to make sense, like a real strict sense to the words that connection is actually a way to differentiate a section. I mean, we have the following formula. So proposition. Sometimes people just define first. Well, okay. Let me not go this way. So anyways, suppose that I have what? Suppose that I have V, which is vector field on X. Suppose that I have point P in X, and I have a curve in X. Right, such that, well, first of all, my gamma of 0 is P, and gamma prime of 0 is V at P. Okay? So I have gamma with such initial conditions. Then I claim then for any section on E, we have the following formula. If I would like to take covariant derivative with respect to V of S, is the same as computing this limit. Limit as t goes to 0, so our usual notion of derivative. But then, well, I have to shift somehow my s from the point P, right? So this I do by the following. I have this gamma, right? So, well, I go away from P a little bit, considering this, right? Well, what I want really, I want to subtract this, right, and divide by t, but this doesn't make sense yet, right? Because these two vectors are there in different vector spaces, right? So I need to move this to fiber at the top of P, right? So that I need. For that I am using parallel translation, but its inverse should be here. Okay. So now let's prove this. Okay, so I have, let me consider some gamma tilde which is parallel with respect to gamma, this gamma that I fixed here, and well, I need to fix some initial condition, right? So gamma tilde of 0, what it will be. So I just put gamma tilde of 0 to be, well, this guy. Well, I fix at the moment I fix some u, which I will then send to 0. Well, not send, but take a limit as u goes to 0. But for now I fix, and then gamma tilde of 0 is just tau inverse. So tau inverse u. So this guy. But since I fix the argument for now, I will call it u. So S gamma of u. Okay. Right. And then, well, then for gamma, and suppose I fix some coordinates. Suppose that I fixed around P basis of local sections, right? With our usual notation, coordinates are xi's and basis of local sections are s betas. Okay. So I just want to use this differential equation, meaning this guy equals to 0. So that's what gamma tilde satisfied. Maybe let me leave it right here. So right. So I have gamma, and t will be parameter that actually is not fixed. So gamma beta prime tilde t plus sum of alpha a gamma alpha tilde of t, and then gamma a prime of t capital gamma alpha a beta equals to 0. Okay, so these are components of gamma as usual, as written over there. Right. This is for any t. So for any t from this interval, right? Okay. And then I would like to see that gamma tilde of u is actually s of gamma of u, right? Just because gamma tilde of u is, just to be a little bit more detailed, is tau u of gamma tilde of 0. Right, and gamma tilde of 0 is this guy. So tau of u and tau of u inverse, they just cancel, and I have this. S is fixed, gamma is fixed. But what I'm saying is that this is actually, well, gamma alpha at u is a known number, right? So actually gamma alpha tilde, of u, this is something which is given once you have s in gamma, right? And I will denote it as f alpha of u. So where f alpha is given function, right? Function defined by s. That means so function defined by s and gamma. And let me erase. So function defined by. So if I have s, then I decompose this s in my basis, local basis of sections, and then f alpha these are smooth functions on x, right? But this is not the point of x, but rather some real number, right? To make this a function of a real number, I just slightly abusing the notation, just write f alpha of gamma of t. This is f alpha of t. Right? So I have a function of a real number f alpha, which is defined by s and gamma like this, and gamma t and value of gamma tilde alpha at my fixed u is exactly the value of this f alpha of u. Okay, so now let me proceed. Also, I have, by the mean value theorem, I have that gamma beta of u tilde equals to gamma beta of 0 tilde plus u gamma beta prime of t, some t star, no, that's just a notation, for some t star between u and 0, right? For some t star between 0, maybe like that, by the mean value theorem. Right. So now we are ready to look at this expression, right? So I need to compute the limit of this guy. So I have 1 over u tau u inverse s of gamma of u minus s of p. And then I take, well, the beta component of that. Okay? So when I take beta component of that, this will be, well, 1 over u, and then this is gamma of beta tilde of 0, that's just by definition of our gamma tilde, minus, and this guy is just f beta of 0. Remember, gamma tilde and beta, they coincide only at u. At 0, they're different functions. Okay? So this is not like a identity. Sorry, I forgot something. No, it's okay. This guy depends on you, right?
Which one?
This one. Yes, so it's all right. Okay. Let's continue. Now I express. So I express gamma beta tilde of 0 through these two guys using this formula. Okay. I will have 1 over u, and then I will have gamma beta tilde of u minus u gamma beta prime t star. And then minus f beta of 0. So now this guy is f beta of u. Right? So what I get is that, well, let me use one more line here. So I'm using now, so it will be 1 over u, and then f beta of u minus f beta of 0. That's one thing that I need. And then I also have this term, where gamma prime I express using this guy. So I just, right, by the way, here I have tilde. I have to write tilde, right, and here as well, right? And gamma tilde prime I can express through gamma tilde and gamma prime using this equation, right? So what I have is so minus over there. So what I have is plus actually. So plus 1 over u, and then sum over alpha and a, right? Gamma alpha tilde of t star. By the way, there is no 1 over u because it cancels with this u. So I can erase this. And then gamma a prime of t star. And then gamma alpha a beta. Okay, so that's what I got. And now I take a limit as u goes to 0. So u goes to 0. Then, well, this guy becomes df beta, well, the derivative of f beta with respect to u at u equals to 0, right? Plus, what I have is gamma alpha a beta f alpha of 0 gamma a prime of 0. Right, t star is squeezed between 0 and u, right? So therefore it goes actually it goes to 0, right? So therefore I can write like that. All right. So now I would like to. So I claim that this can be rewritten as follows. Sum over a, and then df beta over dxa plus sum gamma alpha a in beta f alpha of 0, and then dxa. So all this applied to sum over v b d over dxb, right? Well, it's like dxa evaluated at this guy, I mean. Okay? So that's what where sum over v b d over dx a is my well, it's my v, right? Well, it's my v. Well, this is all at 0, right? So therefore, well, I need to take this is at 0. This is at 0. So this is v at p. Well, this is at p.
So d over dxb or dxa?
Dxb, sorry. Right. So this is just a coordinate expansion of my vector field V, right? Well, basically, which is sorry, I started with V, but here V is just at V is just gamma prime at 0, right? So V actually sits here. That's why you see this term already matches, because dxa it's this gives me VA, and VA is exactly gamma A prime of 0, right? So this terms match. Now I would like to look at this. For that, I just need to write, remember what was F beta, so my D, so this is dF beta of gamma, so this is dF beta of gamma of U, because beta initially is a map on X, right? And this is like a composition with a curve. Then du. So this is the same as, well, it's just the differentiation of a complex function, of a composite function. So this is df beta over dxa, sum over a, right? D gamma a of u du. So this guy is here, and this guy is actually, again, gamma prime of A, right? And I need to take it at 0. Well, here it's at U, but eventually I need to take it at 0. And this is again my V. So if I take, well, this is, okay, if I take this at 0, this will give me exactly a multiplication by VA, which is from this guy. Okay?
Excuse me, I got late for the lecture, so I skipped break to 5-10 minutes. And right now I'm lost. I don't know if this is appropriate. May I ask you to briefly go through the first couple of slides on the main part, something meaningful without the proofs?
But, well, okay, so it was just a recall, right? So we have gamma in the base, gamma tilde, which is in the total space. One is lift of another. S is extension of gamma. And then I recall that gamma tilde is parallel with respect to gamma if such thing happen. Then we had this last time, and gamma tilde is parallel with respect to gamma means just some differential equation on the components of gamma tilde, which is this goes to 0. Then I'm saying that okay, we have unique lift if we fix an initial condition. Well, lift in the sense that well, gamma tilde should be like a lift, but also parallel with respect to this gamma. Then we have uniqueness if we fix initial condition. That's what happened here. Then I define parallel translation, right? So which is like that. So you have base, you have like a total space here, you have like a vector in here. You would like it to translate to here along a curve in the base. So what you do, you consider using this proposition curve in total space, which is parallel with respect to this one. And just, well, I didn't write it very well, draw it very well, so it should be curve which, Well, you see, I don't need these arrows. This is like, so this arrows is bad because this is I just need points. So I have a point in this fiber and I need to translate it somehow to some point in this fiber. So I take some curve which is parallel with respect to this one and see where it ends in this fiber. This, by definition, my parallel translation. And then I say that, okay, actually there's this nice formula which for covariant differentiation. So which is actually like maybe a reason why we call it differentiation. Right? So basically you fix a vector field point and consider a curve with such initial conditions. So it's, you know, value at 0 is p, its velocity at 0 is given by vector field. And then you have, for any s, you have such a formula. And so that's what we're proving.
Okay, thank you very much.
Yeah. Yes. And so we're using basically mean value theorem, right? So we need to write this expression somehow. So we're using mean value theorem to go from gamma tilde at 0 to gamma tilde at u and gamma tilde prime. And gamma tilde prime we express using the differential equation for the gamma tilde, and then you're done.
And can you specify again why at limit we have gamma tilde a at t star equals to f a at 0? So it's like
Here, right?
no, like gamma tilde a at t star. It goes to f a at 0.
Yes. It was somewhere here, I think.
So it's still like it
so-
goes to yes.
So this is what you're referring to. So gamma tilde a of t star.
Yeah.
Yes. So this guy.
Yes.
Right. So this should go to f alpha. Well, here yeah. So it's a good question. Here I'm using that rather t star goes to u.
Oh yeah. That's,
Yeah. And so then I'm saying that gamma alpha tilde of u is f alpha of u, but since u is also goes to 0, it's f alpha of 0.
So as u goes to 0, t
Yeah.
goes to 0 and both u, so it's
Yes, they all go to 0. So u goes to 0, and so therefore t star, which squeezed,
yeah.
I can use it's either goes to u or to 0. It's
Yeah.
all the same. Yes. Right. So let's proceed. Okay. Now we kind of go down from the generality where I have any vector bundle E, and let's concentrate on vector bundle Tx. Right. What is the next? I think the next word is this one. Yeah, so first let's fix some terminology, rather looseness in terminology. So when we say that nabla is a connection on X, it's the same as saying means that nabla is a connection on Tx. Okay, so when vector bundle is not specified, it's really Tx. Okay. So now let again, X be a manifold, so definition. Let X be a manifold with connection. With connection number. Then a smooth curve gamma. It's from open interval to X. Is called a geodesic. If gamma prime of t is parallel with respect to gamma of t. Well, for some reason it is more handy for me to go to open intervals. Well, you'll see in the next statement why, but of course, parallelism you also can define not over closed intervals, but over open intervals. There's no difference, really. Okay, and then another like a part of this definition, what is a maximal geodesic? So a geodesic is maximal if it's not a restriction of another geodesic. If it is not a restriction of another geodesic.
Restriction in the sense that the images of X are one is subset of another.
Yeah, so it's one is defined on a subinterval of A. Like a restriction means like I restricted to some particular subset of the domain. Okay. Proposition. For any p in X, there exists unique maximal geodesic gamma. And let's, for just convenience, assume that AB contains 0 inside, because I want P to be the parameter corresponding to P to be 0, right? That's just my choice. So there is maximal geodesic from this interval containing 0 to X, such that gamma of 0 is P and gamma prime of 0 is V of P. Oh, okay. I didn't fix enough data, so I also need to fix here VP and TPX. Okay. Okay, details aside, it's clear how to prove this. You need to use like some kind of Cauchy theorem again. You have initial conditions, you have differential equation, blah blah blah. But also you need to like to extend it, well, in a good way. Well, anyways, but I still want to go to details just to because I will need some details in the future. Also, I will need geodesic equation, which will appear. Okay, so proof. Well, let me fix coordinates at around P such that xi at P is just 0. All right, and then Vp I can expand in corresponding basis for Tpx, and coefficients, let me just denote them as Vi d over dxi. Okay, so now I need a certain claim that I will jump to another board. So claim. I will refer to this claim as claim star, and I will refer to it not only in this proof. So this claim is the main reason I go to details. So there exists some epsilon, which is positive real number, and open neighborhood V of V1 Vn. Well, it is open in Rn. So V in Rn. So these VIs are given by Vp. So this is the coefficients. Right? Such that for any W1, Wn from V, there exist smooth functions gamma I, and this is, so these are components of my geodesic. So this will be from this to, well, to R. And here I have n of them, so I from 1 to n. Such that so they solve system of differential equations, which system? Gamma I double prime of t plus sum gamma, so this is sum over j and k. J prime of t gamma k prime of t gamma capital J K I equals to 0. And this guy we will have a name for it. It's called geodesic equations or geodesic equation. Okay. It's a system of differential equations because, well, we have such an equation for each I, and this system is of second order, as you can see, and it's not linear, anyways. So because of this, you have like a multiplication of two derivative of gamma. Anyways, I didn't finish the claim. I'm saying that with initial conditions, gamma I of prime, gamma I of 0 is 0, and gamma I prime at 0 is Wi. So what I need, and also, moreover, I'm still not finished, function fi, which is from interval cross v, where v lives inside Rn, to R, which is defined as follows: fi of t w is my gamma I of t. Right, so I'm kind of emphasizing the dependence on initial conditions here of my gammas. I'm saying that these functions are smooth. I don't have, so are smooth.
Excuse me, what does GE stand for?
Geodesic equations.
Geodesic.
Yeah, geodesic equation. Let me.
This is the requirement of being parallel with gamma.
Gamma being parallel, gamma prime being parallel to gamma.
Mm-hmm.
Yeah. Yes. Well, basically, what you do, you take this equation that we had in the beginning of the lecture, which is still wrong because yes, we have tilde in here, right? And instead of gamma tilde, you put gamma prime.
Mm-hmm.
You get this,
Mm-hmm.
which is now not linear and of second degree. Well, this is claim. What I needed from this claim is first explicit form of geodesic equation, and second, smooth dependence on initial condition. So there is some open neighborhood of a fixed point for each fixed point, such that this gives me some smooth dependence of this neighborhood of initial conditions. And so my solutions will depend smoothly on these initial conditions, locally. Okay. Well, the proof of this is not really differential geometry, but rather multi-dimensional calculus. I can really give you just a reference where exactly such thing is proved. And so this just follows, so claim just follows from, well, this is what the theory of ODE, right? This is ordinary differential equation. And so C, for example, Lie smooth manifolds, or introduction to smooth manifolds, and theorem D1, which is exactly about our case, and it's proven there, so to all the details. Okay. Okay. So this is one thing I need. And then, okay, so how to apply claims? So we are proving the existence of such things. So I have my gamma i's, right? So therefore I can consider gamma tilde, gamma bar of t, which is just a curve given by these components.
What are we proving right now?
Yeah, so we are proving this, that there exist unique maximal geodesic. So first we prove that there exists locally, there exists a geodesic. So basically we proved everything, we're just using this claim and we're saying that this will be a curve with such components. And now I'm trying to write this down. So basically I'm taking a curve now inside Rn, right? And then I have U phi, it's my chart where my x, where in which, well, U phi, this is a smooth chart. Around P, right? And then if I take well, we can take epsilon small enough such that this gamma tilde, gamma bar, is inside the image of phi of u, right? So let's take such epsilon small enough. So that I want to consider inverse of phi applied to gamma tilde of t, right? And then I denote this as gamma, I don't know, epsilon or whatever, gamma of t. This is like a piece of geodesic that I have. Well, let me write gamma epsilon. It's not maximal yet, but it's some geodesic, right? This is a geodesic. Just by construction. So this proof existence. Not yet. So this proves of existence of geodesic, but we need maximal geodesic. Maximal geodesic is just follows from what Soren's lemma, right? Because I have partial ordering on a set of all geodesics. Basically, one geodesic is smaller than another if the small one is a restriction of the bigger one. Okay, this is a partial ordering. And of course, any chain has a maximal element, which is just a union of all these curves, right? Take a union. And so every chain has maximal elements, so therefore there exists a maximal element in this set. So maximal geodesic exists by Soren's lemma. Very well. And well, uniqueness, not so interesting to go to dive into details here, but so uniqueness. Let's just briefly discuss.
Она просто единственная решение.
Ну да, но как бы она не обязательно дотянется до всех точек, как бы вот это решение единственное. То есть мне, so what I want, so indeed, what was, so we talked that it just follows from uniqueness in this claim star, which is true, but one additional line should be said is that, well, so basically you have, suppose that you have two such geodesics, right? Maximal ones. And then, well.
But shouldn't be there only one maximum geodesic by itself?
Yeah. So the thing, yeah, my picture is not good. So what I'm saying is that there is uniqueness in some local. So a claim gives uniqueness in some local area, right? So inside this area there's only one geodesic. But what if but we're talking about uniqueness of maximal geodesic, right? Well, suppose that I have like some two maximal geodesics, right? Like gamma 1 and gamma 2. Well, this is why this is the same initial condition, but there exists some T0. I cannot draw, so they should satisfy, so I cannot draw a good picture. They should satisfy. That's what we're trying to prove. But for the sake of contradiction, suppose there exists some T0, maybe outside of this area, such that the gamma 1 of T0 is not equal to gamma 2 of T0.
Maybe this is like a branch.
Yeah, maybe, I don't know. Maybe something weird happens. Yes. Yeah, in principle we could have like maybe something like this. But the thing is that when you have something like this, in a branching point you still have like you still can have some neighborhood. Well, the thing is that, let me not draw this. The thing is that you can just, so you have 0 to T0, right? So 0 corresponds to this point, initial point. And then I have where conditions, initial conditions for gamma met. And this, I need to use that this is compact. So therefore I can cover it by this, so this is compact. So therefore can be covered.
The first point where they do not equal to each other, or just some point?
Yeah. Well, some point. Yeah.
Okay.
Yeah. So they can be covered. Well, we fix this point, right? And once we fix, we say that all geodesic, we have unique maximal geodesic, right? Well, compact, so it can be covered by, well, neighborhoods where, uniqueness in claim star holds. Well, covered by finite number of such neighborhoods. So basically the picture is the following. So you take two, you take your gamma 1 and gamma 2, well, they coincide here, right? And then, you take a cover like this. This is your T0, right? So they coincide here, and so you know that they coincide in an initial condition somewhere here, right? And so therefore they're unique in this neighborhood as well. So therefore they coincide in here. And so they're unique in here as well. And so they're unique all the way to the point so this infinite number of steps, you prove, again, this is loosely speaking, but I don't think it's interesting to have a formal, like strict proof of this. So infinite number of steps. So we prove that gamma of T01 equals to gamma of T02. And so this will give you. Okay. All right. So we have what? 5 minutes. So let me give you definition maybe. Yes, so let me just give you a definition. So in case I would like to include some problems in the next seminar. Maybe so I need to think. Last year I did this. Since we missed last time, maybe in order to accelerate, we will pay one seminar to have more lectures. So maybe like 2 lectures instead of lecture and seminar. I don't know. But okay, let me just give you some definition. So I would like to introduce. So let me give you this proposition. Which is without proof yet, but we'll prove it next time. So for each point in my manifold, there exist neighborhoods n, so this is a neighborhood in TPX, and another neighborhood, actually I just need one neighborhood. So just neighborhood M inside TPX. Well, neighborhood of 0. First of all, of what? Of 0. So it contains 0. Such that 1 is in the domain of gamma v of t, well, this is some notation that I don't want to put into proposition. So gamma v of t, so notation, is just a geodesic from proposition, from the previous proposition. let's recall. So we had this. So we had gamma at 0 is fixed point, and gamma prime of 0 is a, well, v is a some fixed vector, right? And so right, and so v, so here v is inside TPX, right? So v here is our initial condition. So in the domain of gamma v of t, for any v inside n. Anyways, I'm saying that there exists neighborhood inside initial conditions of my geodesics, right? Such that in each direction, I can go to the step 1, right? So my geodesic can be like maximal geodesic. I can never, for example, I can never reach 1 in some direction. So I'm saying that there is a neighborhood of initial conditions such that 1 is always in the domain of this curve. Does that make sense? So what I'm saying is that, okay, let's fix a point. Let's consider geodesics like going outside of this, or going through this, from this point, right? I'm saying that, okay, if I restrict, well, initial condition for velocities, then whatever geodesic I pick, I go to the point, for example, this one, gamma. I will reach a point gamma of 1. So 1 is, gamma of 1 is well-defined point. Yeah, so yeah, 1 is in the domain of gamma v of t.
What about the case where we can reparameterize our curve? We can choose maybe different penetration.
But then the velocity will be different. This is the whole idea actually. So you reparameterize, so which means that you make the velocity smaller such that your parameter is bigger, so you can reach 1. So that's the whole point. And this follows from geodesic equation. Well, I don't have details now, but actually it just follows from the following. Sorry. Gamma v of ct. It just follows from this thing, and you can see from the geodesic equation that if this solution with such initial condition, then this solution of with such initial condition. But that's details we will see. So, but I really need to, if I restrict initial conditions, I really need to reach gamma of 1 in every direction. So for any v in n, and moreover, so such that 1 is in the domain, and the map, and that's where I will use my claim, v goes to gamma v of 1 is smooth. So I also need to make it small enough so it belongs to v from the claim. So smoothness of initial conditions, I will need that here. Okay, so this is my proposition, and well, we'll prove it next time, but what I need from it is this map. So definition, the map, well, it's from n, from here, to x, and it sends v to gamma v of 1 is called, so it's from, so this is a neighborhood inside TPX. So this is from tangent space to manifold itself. Is called the exponential map. And okay, next time we'll see some properties. But now I can use it in symptomistic range. All right, so let's have a break.
Нет.